Okay, so in year 11, extension 1, this is just an extension 1 topic, it's not advanced. Um, there are two components to rates of change. There are what we say is related rates of change. So just any rate of change, anything really, any application of rate of change. And then there's another one that is a bit more specific. It's exponential. So exponential growth or decay. So it's with ease, logs and exponentials. So there's this one here, rates of change. That's anything, which is the hard one. This is the one that you're not going to like at all. Then there's this one, which we have started in logs and exponentials, and we're going to continue that in extension 1 now, but it's exponential growth and decay. This one here, I really haven't had anyone that's had a problem with this. So we shouldn't have a problem with this bit. So you can assume most of your peers as well will not have a problem with this. It's this one here that you can assume a lot of people will have problems with. It's the part that you really want to differentiate yourself, because that would be the difference of you coming first compared to you coming second. This one right here. All right, let's get started. So we're going to start with section 2, of course, because it's the easier one. Okay, it's bigger. All right, let's get started. Where's my pen? There it is. Exponential growth and decay, of course. So with a growth, the idea is it's a simple population growth. The growth is directly proportional to the current population. So in other words, the mathematical model is dp on dt is equal to k times p. Now, the way we read this, just as a bit of revision, is if I had dy on dx, that's just the same as y dash, right? That's your first derivative. First derivative. Okay, so y dash is my first derivative, dy on dx. That means before this, you would have had a y function. Now, we're not sure what the y function is if it says this. This just says that the derivative of the population with respect to time, the derivative of the population with respect to time is equal to a proportion, a letter. We're not sure what it is. We're not sure if it's 2 times, 3 times, 10 times, minus 1 times, but we know that it's some number times by the population, by the original current population. Now this is called the rate of change, just so you can get used to that word. We just call the derivatives before and y dash and calculus, but that is the rate of change of the population with respect to time. Do we all understand how to read this now? Rate of change. So if I ever said this, I'll show you something. Speed. What is speed equal to? What's the formula for speed?
Isn't it distance over time?
Right? So speed equals distance over time. Now you've seen distance over time or things written as speed as kilometers per hour, right? You've also seen that was called a rate. That's the rate of your distance changing with respect to time. We called that speed. Speed is actually y dash. Speed is dx on dt, where x is displacement. Now, we're going to learn more about displacement, velocity, and time and acceleration in year 12. That's the rate of change of year 12. But I'm just trying to show you how something you've done before, which was a rate, right, kilometers per hour, is actually the same as a derivative. They're actually the same thing. So something you learned in like year 8, year 9 is now getting linked to something you're learning in calculus. And I hope that we can see the link soon enough. But for now, all you need to know is when we say this, dp on dt or even dy on dx, it's really a rate of change. It's the rate that the population is changing with respect to time. Now, what we know is that all exponential growth questions are this. dp on dt is equal to kp. That's great. There it is. If dp on dt is equal to kp, we actually can get a solution to this equation, which means you've got to integrate, which is next year. You don't need to worry about that, to this. And it's always going to be this. So I want you to write this down, then the solution to the differential equation is, and then I want you to write this. So write that, and write that, and write that's exponential growth. And obviously we're going to do decay soon. Part of rates of change. Remember, this is extension 1 only. So hopefully it goes in your extension 1 book. The rest you don't need to worry too much. Maybe write, this is also called rate of change. That bit there. Okay. All right. Anyone still writing?
Yeah, just give me a second.
Yep, this one, the way we're writing it, by the way, is P equals P with a little 0 at the bottom, and then E, K, T. So E to the power of K, T.
Yeah, I got it.
All right. Anyone else still writing? Okay. All right, so these work interchangeably. What you've just got to watch out for if the question says rate. Rate specifically means this one here, right? This is the rate. This one here is the actual population. So the population is equal to P naught times by E of K times T. K is a constant. That's a constant. It doesn't change. And T is your time factor. You guys probably remember when we did logs and exponentials, we were using these equations. Okay, we don't need to do any of that. We're just going to jump straight to a HSE question. Let's just get started. All right, that's the best way, isn't it? Let's have a read. This will be the question you will get in your exam. So you don't need more, you don't need less. If you can memorize this question right here and understand how to do it and understand every single step, everything else that we're going to be doing is exactly the same. All right, let's do it. At the beginning of 1991, Australia's population was 17 million. At the beginning of 2004, the population was 20 million. Assuming that the population P is increasing exponentially and satisfies an equation in the form of P equals AEKT, where A and K are constants. So this time, instead of them writing P naught, they just left it as A. It's just a bit easier to write. And T is measured in years from the beginning of 1991. All right. Easy. Anyone not understand what the question's saying? And can you see how that's the same expression we're used to? It's saying at the beginning of 1991, Australia's population was 17 million. And then, of course, in 2004, the population was 20 million. And right now, I show that P equals AEKT satisfies dP on dt equals kp. So pretty much show that when I differentiate it, actually gives me the result that we know needs to occur. Okay, you just differentiate the p-value with respect to t and mask the time factor. So watch it like this. So if p equals AEKT, I have to differentiate this dP with respect to time on dt. Now, I just realized something. We haven't covered, I don't think for your class, how to differentiate exponentials, have we? Have I taught derivative of exponentials on the Saturday class? Yes, no, maybe? I don't think so. Does anyone know the derivative of EKT? No. Okay. All right. Let's revise. Let's do that for a second. So before we can do this, we've got to learn to differentiate exponentials. They're actually very easy, probably easier than your other ones. They work like this. What you want to remember is this: exponentials are always exponentials. So they're always themselves. So therefore, if I differentiate it, I have to get itself. That's pretty easy to remember, isn't it? The only difference between your normal derivatives, which was something like this, and you brought the 5 down, and then you take away 1, you don't do that. What you do, you still differentiate the power now. So what's the derivative of 5x?
5.
5, and then what you do, you multiply by that 5. So that's the number that comes down. So exponentials are exponentials, then you differentiate the power and you multiply that. So a little bit different to these cases. So let's do a few more. Y equals, I don't know, e negative 3x. So then y dash is e negative 3x. You differentiate the negative 3x, which is negative 3, and then it becomes negative 3 e negative 3x. All right, a few more. Y equals e to the power of x squared. Who wants to try that? Y dash equals
2 to the ex squared.
Oh, close. You said 2 to the ex squared. It should be what? What's the derivative of x squared?
2x.
Yeah. So it should be 2x ex squared. And then, I guess one more. I don't know, x minus 5. What's the derivative of e to the x minus 5? What's the derivative of x take away 5? That's just 1, isn't it? Because the derivative of x is just 1 and then minus 5 is gone. So your answer is literally just the same thing. The derivative of ex take away 5 is e to the x take away 5. All right, do we all get that, or do we want some more examples? Emily, do you get this? Angie?
Yeah.
Yeah, makes sense. So then let's have a look at this. This one says EKT. We've got to differentiate that. Well, A doesn't change, right? A is just a constant, so that just gets multiplied, just like any other case. EKT becomes EKT, we know that. And then what's the derivative of KT with respect to time? So what would the derivative of KT be? So obviously it would be just K. And you multiply that at the front. Do we all get that? Or should I do that again? Because you're going to do that every single question will need that. No, that makes sense. Okay. Then obviously don't forget what you're trying to prove. You're trying to prove that it becomes K times P. You already have K there. And then you're left with AEKT. Right? AEKT. But then isn't AEKT just P? So you just replace it. And then you're done. That was really easy, wasn't it? So one more time. P equals AEKT. Differentiate it. Exponentials are exponentials, so there they are. And then derivative of KT is just K. So AKEKT. I took the K out, grouped these two together, and then obviously AEKT is just P. Replaced it. And therefore you just proved dP on dt equals Kp, which means that this P value satisfies the derivative. It works. All right. Then what you're trying to do with these is pretty much get rid of A. You want A as a number, and then eventually you want to find K as a number as well. So that's the technique, and there it is. You can see double I says pretty much what is A, and then triple I says what is K. Because once you've got A and K, you'll have an equation for population. Let's just say that. So now if I say, hey, I want to find the population when time is 50, I can just plug it in. Hey, I want to find the population when time is 70, I can sub it in. But the way it looks, I want to find the population when time is 50, well, you're missing A and K. So the logic to all of these questions will be to always find A and K first. To be able to do that, you've got to go back and read from the top. It says, at the beginning of 1991, Australia's population was 17 million. That means when time is 0, the population is 17 mil. At the beginning of 2004, how much time is that from 1991 to 2004? So just go 2004, take away 1991, should be 13 years. When time is 13, population is 20 mil. Once you know that, you start plugging in. So the first one is when time is 0, P is 17. Let time equals 0, P equals 17 mil, and this is the way it would look. So other than part I, we rarely use the rate. We usually use the actual population equation. So you've got P equals AEKT. You know that time is 0. You know that population is 17 mil. Okay, what is e to the power of k times 0? Well, that's e to the 0. What's anything to the power of 0? Just 1. So then you just worked out that a is actually 17 mil. So your new equation, technically it looks something like this. P equals 17, million, if you really wanted to put those zeros in, and then E, K, T. That's not too hard, is it? It makes sense. Just a matter of you remembering that, yeah, initially time is 0, and that's what you need all the time. Every single question, you're going to get time is 0, initially, time is 0. Initially. That's another word that just means time is 0. Okay. Triple I. Find the value of k. Well, to find k, you'll use the other condition. When time is 13, population is 20. Use other conditions given. So, time is 13, population was 20 mil. So look something like this. Look, that's your new formula, right? Population is 20 million. Equals 17 million. E k times 13, or 13k. Okay, look what you're solving for. You're solving for k, right? And this looks pretty similar to the logs and exponentials questions that we were solving for before. Actually, it's exactly the same as the ones that we were solving before. So we're going to try to solve for k. Does anyone know what the next line would be? 20 million equals 17 million, E 13k. What's the first thing I get rid of?
Don't you get rid of the 17 million?
I agree with you. So get rid of 17 million over 17 million. Cross out the 6 zeros, cross out the 6 zeros, and pretty much you would have 20 over 17, but I'm sure your calculator would have done it for you. Boom, you're here. Now, how do I get rid of the exponential then, Emily?
I have to do ln,
Yes,
so you both sides.
Oh, I'm liking this. 20 on 17 equals 13k. Finish it off. K equals what? What'd you get in your calculator? .0125.
Yeah, I got the same.
Perfect. All right, let's go back now. Anyone want me to go over anything? Anything sound confusing? Forgot what to do, or why we did something, or anything? Any questions? No. Hey, this is good. Okay, that means I've taught it pretty well. You guys are saying all good. That means we're doing really, really well. All right. Now, only want to talk about one thing. I've been hearing from some of your teachers that your teachers are saying to sub this in as k. Please do not sub this in as k. We sub this in as k. Right? So the way to do that, you got to just press Shift, Store, which is on top of the RCL button, and then pick a letter, A, B, C, and then to retrieve it, you press alpha A. You've got to store this number. You don't want to use a rounded answer during your another question. If you use a rounded answer, some questions you might get right, some questions you might get wrong. And the fact that some questions you'll get wrong, I'll never tell you to use a rounded answer. Use the exact answer. So I personally wouldn't put all this into my calculator again. I'll just store it and I'll just retrieve it as alpha A. So I'm going to do that now. Shift store. It's locked in as A. Okay. All right. No questions there. And then predict the year during which Australia's population will reach 30 million. Predict the year. Also worth 2 marks. Okay. Well, that just means I've got my new formula, which now looks like it's 17 million E. I know what my K is times T. So P equals 17 million. E K is 0.0125. You write it, you just don't use it. T. You know what P is? P is 30 million now. And then of course you guys know you can just cross out your zeros. E. All right. And then just solving again for T. You just do it all again. So easy. This was a HSC question and it's every year. It's the same question every single year with exponentials and growth and decay. Log both sides. This pretty much cancels. This comes down when you log, right? Because powers can come down. That's the whole point of why you're logging in the first place. And then you divide. Now, we're going to try to see if it mattered in this case. I'm going to put this in my calculator, and I'm going to put the other one in my calculator, the one I would have had. And we'll see what 2 answers we'll get. Just for your own, I guess, knowledge. See if it mattered in this case. So if I put it over A, log 30 over 17, over A, I would have got 45.43. If I did log 30 over 17 divided by 0.0125, I get to 45.43. Yep, so no matter. It didn't really matter in this case. Well, it becomes 4 really, but not that it matters so much. In this case, of course. So you would have been okay. But you don't know that. So because you don't know that, it's safer to say A. You wouldn't have got 4 marks because the question did say predict the year during which Australia's population will reach 30 million. So it started off at 1991 plus 45.44. So in other words, in 2036, in the 2036th year. If you didn't write that, you will not get the extra mark. In the 2036 year. All right. Any questions? That's 6 marks in your HSC. Right, it's a HSC paper. Let's do it again. We've got no questions. Anyone still copying or okay? All right. Because I've got answers, I might leave that one for you guys to try at your own time. All right, well, we'll do the exact same thing. Now it's going to be a decay question. Decay just means it's the negative. Nothing else changes. So it's exactly the same formula. It's just your population's dying out. So like bacteria and stuff like that, you can decrease the population by modeling an exponential decay. So P naught E negative KT, which means it's decreasing. And I think you guys already now know 2 to the negative X looks like this compared to 2 to the X, which would look like this. So that's an exponential growth. That's an exponential decay. Your population is losing numbers. All right. If you ever see the word half-life, half-life of a quantity decay indicates the time required for the quantity to decrease to the half of the original amount. I think that makes sense. It's just a lot of students have a question about that. A half-life just means half of the original amount, half of its life, half of the population growth, whatever it is, half of the original population. Okay, let's read this 2017 HSC question worth 5 marks. Exactly the same. Like I said, don't stress about it too much. Don't change. Nothing really is changing. Just do it all again. So let's have a read. Carbon-14 is a radioactive substance that decays over time. The amount of carbon-14 present in a kangaroo bone is given by CT equals AEKT, which we already know. We know that's the formula. I mean, you could have written A, and then they would have changed that to A naught, just so they're not the same. You could have used population, P equals A. They just use C for carbon, I'm guessing. But CT equals AEKT, where A and K are constants and T is the number of years since the kangaroo died. Show that CT satisfies DC on DT equals KC. How do I do that? What do we do for I? Show that CT satisfies DC on DT. Novak, what would you do? DC on DT equals KC. Show that this satisfies that.
Sorry, so you know that A.
What is C equal to? Firstly, start with C. C equals
to AE KT.
Perfect. So therefore, DC on DT equals
AK
AK
EKT.
EKT, and then you know that obviously K you can just take it out. You're left with AEKT, and what does AEKT equal to?
C.
And therefore, you just
Okay.
proved that
Yeah.
DC on DT is equal to KC. Very easy. Will be the first question. Has to be. So 1 mark easily you can get by just walking into your extension 1 paper, already knowing how to just differentiate this. Double A. All right, double A. And then pretty much after that, unless the question says rate somewhere, which I can't see here yet, you're not going to use this formula. You're going to more use this formula here. So back to it. Back to this formula. After 5,730 years, half of the original amount of carbon-14 is present. Show that the value of K corrected to sig figs is negative 0.00012. Oh, very nice of them that year. What year? 2017. They actually said show that that's 2 sig figs. It would have been nice to say just find it to 2 sig figs and see if students actually knew how to write it to 2 sig figs. But anyways, they were nice. After 5,730 years, half of the original amount of carbon-14 of the original amount of carbon-14 is present. Show the value of K is this. Okay, anyone know what T equals to? Pretty obvious. Novak? We might as well continue this question actually. What is T equal to?
Would that would that be half of the original? So okay.
No. So time is still the time. Time is not changing.
Yeah.
So time is what? How many years?
5,730.
Yeah, so that doesn't change. Half of the original amount of carbon-14 is okay. So what does C equal to? How much is left in your carbon-14? It's saying half of the original amount. And what letter would be the original amount?
Wait, what?
What letter would be the original amount?
C. Yeah.
No. No. So the original amount is actually A. I didn't want to say it just before because I was hoping that you would see something. So look, initially,
Yeah.
what does that mean? Time equals?
T equals 0.
T equals 0. What happens every time? You're going to have 0 up here.
It becomes 1.
Yeah, so what's going to happen every time for A?
Oh, okay. Yeah, got it. 1/2.
Initially,
Yeah.
when time is 0, A will always equal to C, or A will always equal to your initial population.
Oh, okay. I
Always.
see it. Yeah.
All right, you guys. So when time is 0, doesn't matter if it's -0 or 0, it's always going to be your A, your A, and that's why we sometimes use A naught to try to remind students that that is when it's at 0. Your A value, anyways, that's always attached, will always equal to the initial population, initial carbon amount, initial bacteria, whatever you want to call it. So when this question is saying half of the original amount, the idea is what more students had to know is that C is equal to half of A. And that's the only way you would actually get rid of A when you go on to sub it in. Otherwise, if you only knew C was like 5, let's say, you're still going to be missing you're going to still have A missing. But in this case, half A equals, why do I write half again? Half A equals A E K T. You can actually get rid of A and you can solve for T. Can you see that?
Yep.
All right, and then what would you do after
LN
this?
both sides.
LM both sides. And then can you tell me straight away, you can probably see, you're going to divide it, aren't you?
Yeah, yeah.
So you might as well do it in one line. Especially being extension students, this has to be done in one line. Like that's it. You guys got to start realizing when you know that's cancelled out, you're going to log, there it is, you're going to divide it. So just get it out of the way. Plug it into your calculator, and let's get an answer. There it is, and I think we agree with what they asked us to show. I got that, and that's exactly what we needed. All right. Any questions? Cool. The amount of carbon-14 now present in a kangaroo bone is 9% of the original amount. Find the number of years since the kangaroo died. Give your answer correct at 2 sig figs. All right, Novak, what do you know now?
Find the number of years since the kangaroo died.
Obviously, what letter are you finding? That's good to know.
Number of years.
Yep. So what letter?
Is that time?
That is time.
That's T, yeah?
Yep. You're finding T.
So then you solve for T again.
Yes, you're going to solve for T. Well, we already know what K is.
Yeah.
So that's fine as well. We're missing A and we're missing C. But it says something here. The amount of carbon-14 now present in a kangaroo bone is 9% of the original amount. So what does C equal to?
9%
Of,
of the original amount.
which is what? What's the original amount?
Yeah.
No, you came to the same problem as before. Anyone can help him out? What's 9% of the original amount? 9% of what? What was the original amount again?
A.
A.
Oh, and C equals A.
Yes, C. Well, that's original amount. Original. Right? Initially, when
because
time
T
is 0,
equals
this would be
0.
the original. So when you're saying it's 9% of the original amount, that means C is now 9% of A. Do you get that?
Yeah.
Yeah, because A is your original amount. That's what you're finding every time. You'll see it once you do numbers, but there you go. Triple I. The idea is all you're going to write is 9% of A equals A, E, K, which is decreasing. Now you guys know that because it's a negative. You see how you didn't bother you, even if it's a decay question? Cross out the A, log both sides, divide it. You're done. Log 9% over negative 0.00012 equals T. Novak, easy?
Easy, easy.
Easy. Just that beginning bit.
Just a C equals original A.
Yeah, that's one. Log 9%, divide negative 0.00012. Wait, what happened here? I've done something wrong. 2. Wait. Carbon-14 is the indicator. The amount of carbon-14 present in a kangaroo bone is given by this. Now present, the amount of carbon present in kangaroo bone is 9% of the original amount. Oh no, that's not wrong. I don't know how he got his answer, which actually doesn't make sense because we know 5,000 years it was half. He's got his answer wrong. I'll tell him about that. What'd you get on your calculator? Novak?
I didn't actually do it on the calculator.
Come on.
You went 10.
Log 9% over negative 0.00012.
Log 9% over negative 0.0. 2006.62.
You sure?
Yeah, log 9% over negative 0.00. What? 20,000.
Yeah, that's better.
6.21.
So 20,000. And I think the question said write it to 2 sig figs. So it should be just 20,000 years. Make sense?
Yeah.
So, and I know his answer is wrong because obviously we know that it took 5,000 years for it to be half the amount. So it's going to be 9% of the amount. It's going to take a lot longer, obviously. So 2,000 years. 20,000, sorry, in this case. That's fine. Let's go do another one. Let me see what's after this. Is that it? That is it. And Newtons. Okay. So let's have a read of this. Trout. Question 16. Question 16 is the last question of the HSC. All right, so last question meaning hard. Meant to be hard. But don't forget, this was, well, anyways, it doesn't matter though it was in the 2 unit, because this was a year 12 topic, but they brought it down to year 11 extension 1. So hard, yeah, I mean, it's hard. That's it. Let's just do it. Trout and carp are types of fish. A lake contains a number of trout. At a certain time, 10 carp are introduced into the lake and start eating the trout. As a consequence, the number of trout, N, decreases according to this. So we understand that? The carp, there's 10 carp that got started. They got introduced to eat the trout. So that means the trout will die out and the carp will increase. Where T is time in months, and after the carp got introduced, the population of carp obviously will increase according to this. dP on dt is equal to 0.02p. So this looks like dP on dt, which equals to kp. The reason why it's question 16 is because you had to know that that was kp yourself. So therefore k is equal to 0.02. And that's what a lot of, obviously, you know, Band 5 students wouldn't pick up on, because they know most of what we've just done, the basics, but they don't link the two together. Band 6 students, they get it, that's okay, and that's pretty straightforward to see. So just be aware of that. And then from that, of course, they've also memorized the formula, which they know looks like this. All right, let's start with the first one and see. I. Shania, you there? Let's do I together.
Okay.
How many trout were in the lake when the carp were introduced? So how many trout were in the lake? All right, so that means we're going to use this formula, trout formula, not the carp formula. So we've got N equals 375 minus e to the power of 0.04 t. How many trout were in the lake when the carp were introduced? What does that mean? What would time be when the carp were introduced?
0.
Time is 0. Simple. Don't overthink it. Initially, beginning, whatever you want introduced, just means time is 0. So therefore, n equals 375 minus e to the power of 0. What's the answer? Be careful.
375 minus 1.
Beautiful. Good job. 374. Done. That's how many trout were in the lake when the carp were introduced. Good job. Double I. Let's do it one more time and then show it all good. When will the population of trout be 0? All right. What does when mean? What letter are you trying to find when it says when?
N.
Ooh, no. When?
Oh.
If I asked you, yeah. If I asked you, when will you be there? What would your answer be?
At 3 o'clock.
Yeah. So in terms of time, right? That's it. So when, it's important to know that because a lot of students actually have problems with that bit and they don't know what letter they're looking for. But obviously when saying when you're looking for time, look at the equation you've got. If you want to find time, that means you have to get rid of n. What will n equal to?
0.
0. Simple. 375 minus e to the power of 0.04 t. And then what would you do here? You're trying to solve for t, of course. So what would you do first? It's up to you. You got two things. Either moving this guy or moving this whole thing.
Move the E, I guess.
What do you want to do?
Get rid of the 375, move it to the side.
Fair enough. And then you're here. Now. Those two out, wouldn't you?
Yep.
And then what would you do here? 375 equals E 0.04 T. How do I get rid of the E?
A limit.
You've got log 375 equals 0.04 T. And then how do I get rid of the 0.04?
Divide it.
And you found the time. I'm just going to plug it into my calculator. That's good. Thank you. Log 375 over 0.04, 148. So when it says when will the population? What was T in terms of? T is T is the time in months. So when T equals to 148 point, let's say 2. So the 148th month. Now, because it's worth 1 mark, if you just wrote 148.2, you would get you'll get full marks for that. In this case, if it was 2 marks, you wouldn't get 2 marks. If you just wrote T equals 148.2, you'd only get 1 mark because you didn't actually say, you didn't answer the question. Just like I asked you, when will you be there? You said at 3 p.m. You wouldn't say T equals 3, right? So kind of the same concept with this. When we're asking a question like this, you've got to answer it with, I guess, like English. I don't know. It's normal language. Okay, so be aware of that, you guys. It was back in 2008 where they stopped accepting answers like this and they started saying you've got to actually answer it properly. Okay, triple I. Sketch the number of trout as a function of time. So we've got to sketch this. Sketch n equals 375 minus e power of 0.04 t. So of course that's your y value and that's your x value. Time can't get 0. That's why I didn't bother drawing that. But there you go. Okay. 375 minus e. I'll let you guys think about that for a second and see if you can pick up on what you would want to do or how you would draw that exponential. All right. Any ideas? Queenie, do you know how to draw this up?
I'm unsure.
Completely, or you think you kind of know, and then do you know what's
not really.
at all? Okay, fair enough. Yep.
Sam,
Yeah.
I'm not sure, but would you just put 374 for N and then 148.2 for T and then just draw like downwards curve?
148.2. Right, because you said like this one here.
Yeah.
Haha, I like your logic. I see what you're saying. Yeah, no, I can't give that to you.
Fair enough.
Because you said, yeah, because what you're finding, you're saying, oh, when time is 0, 374, and when n is 0, time is 148.2. That's your logic?
Yeah.
Yeah, I can't, because I'm not going to give that to you just yet. No. But good, yes, like, it should work. There should be nothing wrong with what you're saying, but you're missing something that I would have preferred to see first.
Yeah, fair enough.
E to the power of 0.04t. How would you draw that bit firstly? Just E. Forget the negative. How would that have been drawn?
Isn't that an exponential?
Okay, so that would have been looking like this.
Yeah, but it's negative.
Okay, so but it's negative now. So how would you have drawn a negative one?
So you would flip it.
About X or Y?
X-axis.
X-axis. So it'll look like this.
Yeah.
Where does it cut?
negative 0.04.
No.
No?
No. The 0.04 doesn't matter. When time is 0, it'll still cut at -1.
Oh,
Where's-
yeah, because e to the power of 0 is 1. Yeah, yeah.
Yeah. What's your asymptote?
0.
At 0. Now what happens when you do 375 plus all of this? What do you do to that? Say it again.
Move it up.
Move it up. So what's -1 plus 375?
74.
374.
And then where's your asymptote? See, that's what I wanted to hear. More
Fair enough.
than your one, because then that tells me you actually understand what's happening to the sketch.
Yeah.
So, I mean, it's starting like that, and it's doing that, which is what you said.
Yeah.
It's not a problem. It's more, if we don't really see the asymptote bit, we know that you didn't actually know how to sketch it, and we'll give you probably, oh, it's 1 mark again. All right, you're lucky. In this case, you probably would have got the 1 mark. You wouldn't have. It's 2 marks. There'll be a problem. 148.2. All right, and I hope that's good revision for everyone to see that that's how I would have drawn it. Basic exponential is this way. Negative, flip it down. Plus 375, shift it up. So that should be stock standard for you guys by now. IV. When is the rate of increase of carp equal to the rate of decrease of trout? 3 marks. So IV, rate of trout equal rate of carp. Now you got to be careful. That's not when does the population of this equal to the population of the other one, right? It's rate. So you already know the rate of carp. The The rate of carp is 0.02p. That's already done. We get that? And remember, that's the key word. When you see rate, you think, oh yes, dp on dt, or dc on dt, or whatever. It's just derivatives. Rate just means derivatives now, to you. All right. So 0.02p. When is the rate of increase? Yeah, sorry. So that one, n. We haven't differentiated it yet, have we? We've got to differentiate that. So n on the side here, n equals 375 minus e 0.04t. All right. Can someone tell me what dn on dt would be? What would happen to 375? Andy, 375.
I'm not sure.
Derivative of 375. If I came up to you, I said differentiate 375 with respect to time. Is there even a t there? Nope. So what should this become? All right, Andy, here you go. If I said differentiate this, what's the derivative of 2?
Yeah.
Plus derivative of x?
1.
So constants that don't have x's just became 0. Constants that are not attached to time are just going to become
0.
0. So 375, gone, nothing. This one here has the time, so minus. Now, exponentials are exponentials, so what should this one become, Andy? At least. E to the power of what? Not getting it?
No.
E to the power of 0.04t, because exponentials don't change. They become the same, and then all you've got to do is just differentiate this. So differentiate 0.04t, which is 0.04. Do you get how I got that? 0.04 from this? Or not? If I said y equals to 0.05x plus 5x squared, what would the derivative of this be? Well, the derivative of this one here with the x is 1. 1 times this is just this itself.
Yeah.
Right, we decrease, and then plus, you bring the 2 down, that becomes 10x. So same thing, it's just with t. So what's the derivative of 0.04t? Well, that'll just be 0.04. T is your x now, because this is your t's. It's on with respect to t. So your dn on dt is actually negative 0.04. E. Let's do another one again. If I had y equals e to the 5x, just remember that becomes derivative of 5x, which is 5. And then the exponential does not change. That's a good thing. Like, it's meant to be simpler than your normal ones, because exponentials are exponentials. They're always, and then all you've got to do is just the power, differentiate. All right, Andy, that makes sense now?
Yeah.
So the rate of trout is that, and then we get negative 0.04 E 0.04t. Which equals to 0.02p. Okay, what letter don't we like from all this? Let me rewrite it again. I don't really like it like that. What letter don't we like, you guys? Because remember, I want to solve for this eventually. And what was the question? It says when. So I'm obviously solving for time again. So what letter don't I like?
P.
P. So somehow I've got to get rid of P. Well then, but you guys know, so we don't have it, just so you know. What you know is this formula that I write here. You're meant to have known P is actually AEKT, where K is 0.02. So let's get down here again. P is equal to AEKT, where we know that K is 0.02. And the only thing we're missing is A. We would like to get rid of A as well because, you know, you're trying to solve for T. Okay, so then you go up. You're like, all right, A was what? What was A again, Novak? The definition of A.
The definition of A.
Yep, the definition.
A equals C initially.
Well, you don't have to say C. In this case, it'll be A equals to
P.
P, technically, right? A is equal to the initial, say it like this. A is equal to the initial population. It's probably better to say it like that.
Yes.
So, what's the initial population of carp? Now read, unless you know the answer.
Trout and carp they contain in ton. 10 carp.
Yes, right? Initially, there are 10 carp.
Yeah.
That's how you'll introduce that. And that's when, look what question you have to introduce it. IV. You had to go back and reintroduce that number there.
Oofed.
Yes. This is why it's the last question. This is why I keep saying band 6. You guys got to learn to do it like this. Exam questions, no textbook questions. A is equal to 10. That's the initial amount of carp. And now you've got your p-value, and I think from here onwards, we should be pretty good. So let's have a look. 0.02 and then P times 10 E. All right. Oh, actually, still some serious algebra going to happen, but let's see. Obviously, I would change this one here to 0.2. I'm sure you guys would have done the same thing. Just multiply them together. Now you're here. All right, what letter am I trying to solve for?
T.
So what's your golden rule when you're solving? What's the first rule you would have got taught back in like year 8, year 7, when you're solving for letters? What do you remember? It can be wrong, it doesn't matter, just say, what do you guys remember? What do you remember with solving? What are the rules?
Factorize out.
Factorize out, what else?
It must be
Make
equal
it
to
the
something.
subject.
It must equal to something, what did you say? Again, Emily?
Making it the subject or something like
Making
that.
it the subject, maybe having it on the one side, like letters on one side, numbers on the other side. You would have learned to do opposites always, and so on. But the biggest one there, I think, would be what you guys just said. Making it the subject, making T on it by itself on one side, and the numbers on the other side. And that's the same logic here. So whenever you've got, you got a T here and a T here, like, what? That's not allowed. So what you're going to do, I'm going to bring this guy over here, and obviously I'm going to bring this guy over here. Something that I hope you would have done with x's anyways, right? But obviously a little bit different with your exponentials, but same idea. You bring 0.2 over, so it would look like this. Numbers on one side, see? Now you've got your letters on the other side. It's probably better than factorizing. If you wanted to factorize, wouldn't have worked for this question, unfortunately. I can see it. I know what factorizing does. Sometimes you can bring both of these over. Would not have worked because you still would have had an exponential. All right. Anyways, we're at this stage. This one here simplifies, so that's good. Negative 0.04, 0.02. I hope you guys are also realizing something. It's got nothing to do with rates of change now, right? Rates of change. I mean, this particular topic was, I mean, maybe you could say the first line and knowing how to introduce it all and understanding that that's the initial population and whatever. But eventually, this bit here that's actually hard, it's got nothing to do with rates of change. It's all algebra. So like even the stuff that we've done before, I mean, look at all this. Minusing, dividing, logging, it's more algebraic based work rather than specific rates of change based work. Subbing in time is 0. You're not really doing anything that is rates of change based. But anyways, now, what do we know we can do when the bases are the same to the powers? What can we do to the powers? Bases are the same, divided.
Subtract.
Subtract. That's an easy one. 0.02 take away 0.04 gets me negative 0.02t. Now something's happened. Because I know you can't log both sides. Why can't we log both sides? No, no idea. All right, then log this, you guys. Go ahead and try to log that.
Can't log a negative.
You can't log a negative. So that failed, didn't it? How am I going to fix this up? How am I going to fix it up? How am I going to fix it up? There must be somewhere I've done it wrong, and I just realized because, yeah, sorry, fix up now. When is the rate of increase of carp equal to the rate of decrease of trout? So you don't actually need the negative rate. It's already a rate of decrease. Rate of decrease. That's negatives there. That negative is there to say that it's a decrease, right? So when differentiating dn on dt, when you get that, so like, let me show you something. So go up, go up, go up, go up, go up, go up. Look at this question. We found that the rate is kc, right? Then you went and found that k was negative, and the reason why k is negative is because you are decaying. But the rate itself is just kc, rate. So that's my bad. I mean, not a hard thing to fix up. That means just this rate of trout should have just been this. That's the rate of trout. If you wanted if it's decreasing or increasing, then of course it's decreasing because of the negative, and carp is increasing because it's positive. So you're only interested in the rates being the same. You're not interested in the sign. Easy fix. Here we go. ln 1 on 5 equals e negative 0.02t, and then of course log this side, so this cancel out, we divide it, and we shall get the answer as log 1 over 5 divided by negative 0.02, t is equal to 80.47. I always stop there. I go back to read the question. When is the rate of increase equal to the rate of trout? What is t in months? In the 80th month. All right, and last one, B. When is the number of carp equal to the number of trout? When is the number of carp equal to the number of trout? That is now this n equal to, so n equals 375. So n is equal to p, let's say, 375 minus e 0.04t must equal to the number of carp that we found here, 10e 0.02t. 10e 0.02t, and you just go do it again. All right, what would you do at this stage if you had an equation like this? Same logic, right? You would probably plus this over. and you end up with this. But what you have to remember, as you're doing exam questions especially, you see here, and then some of you might have said to factorize, but as you factorize, you would have still had an e. What you and plus is equal to 375. When you factorize, it's got to equal to 0 for you to solve. What you guys want to remember when you're doing exam questions, especially as you learn to do more and more exam questions, if they're in question 16, let's say, and they're the last question of the paper, it doesn't mean, and it's the last one, like V, it might look simple. It means that there's always going to be a hidden trick to it. So when you get a question like this, there's obviously something there that a lot of students would miss. Anyone see what I'm talking about? Maybe if I rearrange it. How do we solve for t here? I mean, that was a hard one already to understand that. Now, how do we solve for t here? You can't say, oh, letters on one side, because it's just not going to work. Because there's a plus 10e there, and these are different powers. Whereas this one here, I mean, you could just divide it. Any idea at all? Anything? Something has to come. I don't want to give the answers because I'm worried if you get a question like this in your exam. Will you think about it, and will you be able to narrow it down to what is required and what you've learned? So give me some ideas. Maybe Anouk, just say a few things that you know to solve. Solving. What are a few?
Is it like the thing let m equals e some?
It is exactly that one.
Yeah.
But did you know that, or was that just a good guess?
I sort of knew it, but
okay. Otherwise, solving. What are the words that you associate with solving?
it has to be equal to something. So
has to equal to something.
It's equal to 0.
Yeah. And then what else? What other words? Like I think about trinomials. I think about quadratics.
Yeah.
You know. What else? Anything else you can think about with solving? Completing the square.
Oh yeah.
What you just said is another one. Substitution. Simultaneous equations. That's solving.
Yeah.
So you guys got to be aware of that. So that's how I would do it if I was in my exam. And if I was stuck, I'll just be like, all right, solving. What are the things I know? Okay, quadratics. Oh yeah, 1, 2, 3. Hey, and then maybe I might have just got out the fact that this term here, if I squared 0.02, I would actually get 0.04. And then I realized, oh yeah, these are actually the same. It's just that's squared, that's itself, and that's got nothing. It's just a constant. But yeah, it's exactly what you just said. So I'm just gonna find some room to write it in. All right. So let's do it here. Let m equal to the middle term. That was the trick. Let m equal to e to the 0.02t. So therefore, this becomes m squared plus 10m minus 375. If you're not sure how you can get that as m squared, just do it here on the side. M squared is this one's power of 2. You know that these will multiply, power, so you just get 0.04. Solve this one. That was a good guess. I just did this divided by 15. It worked out. M plus 25, m minus 15 equals 0. And then, of course, m equals negative 25 and m equals 15. Sub it back in. E 0.02t equals negative 25, which you can't because you can't log a negative, so that one won't work. E 0.02t equals 15. Log both sides. And then divide by 0.02. and you're done. So you can see this kind of equation solving, it's going to be there every single question. You know, logging and dividing, it's always there. And then again, you're just going to sub that into your calculator and finish it off. 135, and then you'll just read the, I think it said, when is it? So in the 135th month. If you want to write down the question on paper, that was 2013, 2-unit HSC. I'll just scroll down again. Everyone for time, I'm doing well. Okay. All right. How are we feeling about this so far? Confused? Starting to get it, or what's the go? What bit is the most confusing? Is it the derivatives? Is it the solving? Obviously, I mean, this was harder because it was it was a question 16. But yeah. So what's the hardest bit for you guys? I just need to know so I know what to focus on more.
I found the bit in question 4 where you got rid of that negative somewhat confusing.
Yeah, so the fact that it's just a rate and
Yeah.
you don't need to worry about the negative bit. Yeah, I get that. That comes through as you start to understand the idea of a rate compared to the fact that it's a decreasing rate or an increasing rate and so on. But that's okay. That will make more sense as time goes on. That's okay. If that's all. That's fine. Anyone else?
I found it all right. It's just like sometimes having to think out of the box, like you wouldn't have
Yes.
thought to do it like that.
Look, and I think that's a question that's been rising with some of you now. You guys are saying, "Oh, we need more questions" or whatever. And believe me when I say this to you, all you need to do is your HSC questions. And if you're able to execute this, so like tomorrow, wake up and actually try to do this whole question again. You know where it's from, 2013 to an HSC, question 16. And if you're able to execute the whole thing yourself, then perfect. If you're not and you get 30% there, then you know you still need 70% to go. Then the next day you'll do it again and you might get to 50%, 60%, you've got 40% to go. That's what I used to do. I used to not move on until I can do one full question and get it to 100%. Because you don't need more. What you need is just the one and perfect it. So that thinking outside the box, you're not thinking outside the box just because you haven't exposed yourself to these styles of questions. And when you do, like you've seen one today, you forget about it tomorrow because tomorrow's questions don't have it. But if you do the same question again tomorrow, your brain will start thinking like that. That's why you guys always hear me say, do this question and execute the whole thing. And if you're able to do it, you'll be fine in your exams. Because I know, especially if you can do a question 16. If you can execute this whole question, you'll be fine for any other question because it's not going to get any harder than this. So you don't need to go and do all your textbook questions and all your teachers' questions. You don't need that. You don't need all the questions. I can send you 500. You won't need it because it won't get any harder than this one. But anyways. I get it, Novak. That comes through time, and if you do what I just said, just repeat, you will be absolutely fine.
Yeah.
All right. Last bit of growth and decay. It's called Newton's laws of cooling. Now, it should be the last bit, I think. Let me just make sure. Yep. So with Newton's laws of cooling, there's just an extra component. Equals the extra component. So the mathematical model to it is this: the population is changing with respect to time as K multiplied by P minus A. So it's not just P. So we were just doing KP. Now it's K and P minus A. So sorry, this is called Newton's laws of cooling. Newton's laws of cooling. Or some people just say modified exponential growth and decay. All right. So the only difference is the fact that it's got this A. So your new formula for population is not just BEKT, it's A plus BEKT. Just one extra term, you're just adding A. And I think you guys can just straight away obviously understand that population is not going to just be according to one variable. You know, there's multiple variables, A, C, D, and they don't always have to be linear. They could have been like D sine theta and so on, or sine T and whatever. That's you're never going to see that until university, if you ever need to do it. But just saying, so we're going to add one extra variable, and that's as hard as it gets in both year 11 and year 12. It doesn't get harder than this. But that extra variable is what we just say is constant, mostly room temperature, room or air temp, temperature or constant room air temperature, constant room, maybe constant population. If you had that constant population, you know, if that wasn't changing, you'll see what I mean in a second. There we go. Questions will almost always require students to, and I think we've said that. Always we'll ask you to differentiate it, then find A, then find K, then find B, and then find the particular time. Come on, if we're teaching it like that. That means we know that that's pretty much what's going to be in your exam. 1, 2, 3, 4. You don't need more, you don't need less. You just need to know the one question really well. So the way it's working is there's a boiling kettle. Initially, that kettle's the water in there is 100 degrees Celsius. It's allowed to cool to room temperature set at 22 degrees. The logic to it is if that value there would be your A in this formula. Because if I poured water into a mug from 100 degrees, the idea is eventually that water will cool down until it's back to room temp, which is 22 degrees. And that's what that value of A is going to be now. And of course, that's the same thing with decay. So I think the best thing is just to do a question. So let's have a read. In a kitchen where the temperature is 20 degrees, Stanley takes a kettle of boiling water off the stove at time 0, of course, initially. 5 minutes later, the temperature of the water is 70 degrees. Show that T equals 20 plus 80 E negative KT satisfies the cooling equation of this. Okay. A. T equals 20 plus 80 E negative KT. What's the first thing I do?
Bring down the negative K.
You're not saying it right. You're right. What you just said is not wrong. It's just.
I'm not saying you're right, yeah.
What did I want to hear on the left-hand side?
DT over DT.
Yeah, that's what I want to hear first. So
okay.
D capital T over DT. So differentiating temperature with respect to
Time.
It's important to read that. Now, what's the derivative of 20 with respect to time? 0. And then now you say, yeah, bring it down. So now becomes negative 80K E negative KT. Yep, I'm happy with that. And then again, the answer is always going to be in front of you. Look at it, what you want. You want negative K bracket T take away 20. Okay, what are you going to obviously take out of this?
The K.
Negative K.
Negative K, yeah.
If it says negative K, you take out negative K. If it's positive K here, and this still says negative K, you still take out negative K.
Yep.
Just like these ones. Remember how I said force a negative out?
Yeah,
So
yeah.
you had this, you force it out. So you would write negative x squared. So same logic. All right, wait, let's not confuse anyone. Back to here. Negative k, and then you're left with 80 e negative kt. And then can you see what 80 e negative kt equals to?
dt on dt.
Ooh, wait, 80 e negative
Oh,
kt.
80e. That would be t on 20. T on 20 would equal.
T minus.
T minus 20 would equal 80e.
And then you're done. How easy was
Sam,
that?
do you
Yeah.
have to write dt on dt, or can you just write t dash?
No, cannot write t dash. Good question. Let's talk about that for a second. So when we were writing y equals, I don't know, 3x plus 2, we're writing y dash. Now y dash is obviously a derivative, right?
Yeah.
Now, we weren't writing dy dx just because it's a bit easier to write y dash. Once it comes to application questions like these, the problem is t dash kind of means dt on dx, which is obviously wrong. It's meant to be with respect to time. So to avoid that, we are using actually d capital. You have to use d's. Now, if your teacher does decide to do dashes, don't do it, because in the HSC you will lose a mark.
Okay.
So for your y dash and f dash, not a problem. Once it comes to application questions like this, applying rates of change, no, not allowed to write t dash.
Okay.
And you'll even see that once we start next week, we do the other rates of change. You'll see it's actually impossible for you to use dashes, because this one here, you're going to split it up into 2 or 3 different ways.
Oh,
And
okay.
if you had t dash, it's just impossible. You won't be able to do it. So yeah, good question. No, you can't. You have to write d. D capital T on dt. It didn't matter with y's. It matters here because applied. All right, easy 1 mark. B. Any questions about that? All right, B. Find the value of k. Well, okay, to do that, again, we go back to our original equation. I think we know that by now. There it is. What do you know? 5 minutes later, the temperature of the water is 70. What do we know? Someone tell me. 5 minutes later, temperature 70.
We know time and temperature. Time is 5 minutes, and you got 70 degrees for the temperature.
So then, what would you write next line?
You just sub those values in.
Say it.
70 equals 20 plus 80e minus minus 5k.
Yeah, we don't write K5.
Yeah.
5. All right, and then of course, as before, look, it's exactly the same, just solving for K. What's your next step?
You minus the 20 over,
And then?
divided by 80.
And then?
You would use ln.
Nice, and then?
And then you have a minus 5, right?
Yes.
So,
Divide.
yeah.
Good. That is where I need you to get to. You must be able to do it in one line, because all the kids at the top schools are all just doing it with one line. There's no way they're all doing it slowly. So let's say that again, exactly what Anouk said. He said 70, take away 20. So you in your calculator, you're just going to write 70, take away 20. Then you would have looked at this. You're like, all right, I know I would divide this. So just write divide 80 on your calculator. Just say 5 on 8 now. Then you would have got to E. You say, I've got to get rid of that. I've got to log it. Answer. Then you're like, I got an extra -5. I would have divided by -5. If you guys are able to do that, we should all end up with this. Anyone want me to actually do it? No, we're good. That's really good. If you're really able to do that, 70, take away 20, divide 80, log it, divide -5. You're pretty much you're doing it as fast as anyone can do it. Okay. See, fair enough. See, how long will it take for the water temperature to drop to 25 degrees? How long? Again, you're trying to find time. So the formula is T equals 20 plus 80E negative 0.094. But again, don't forget, we don't use it. Keep it exact. Shift, store, A. All right, what was the temperature? 25. You just do it again, don't you, Anouk? Same thing. Take away, divide, log, divide. So let's do it. 25, take away 20. Divide 80. Log, answer, divide negative alpha A. All right, I got my time as 29.49, so 29.5. How long will it take for the water temperature to drop to 25 degrees? 29.5 minutes. And then D. Sketch the temperature. Any problems with that one? Sketch the temperature time function. No, all good. That's temperature, Y, and this would be X as your time. Again, just look at it. Where is it? There. T equals 20 plus 80E negative 0. All right. How do we draw this one now? How do we draw this function? Look at it carefully. E to the negative. How would you draw that one?
You'd flip it about the y-axis.
So it looks like this, cutting through 1. When you multiply it by 80, it's going to cut at 80, but it still hasn't shifted anywhere. So just looking like this. Yep. And then what do you do with the plus 20?
You shift it up by 20.
So that means technically that's going to be a 20 of an asymptote there.
Yeah.
And then
And
instead of at
should be
80,
100.
about 100. Oh, missed it. And if you think of it logically now, I know I did give you guys the answer before. I did say that that 20 degrees, that A value there, is just the constant room temperature, right? Look what's happening. It started off at 100 degrees, and eventually as time approaches infinity, your boiling water will reach, your room temperature will reach 20 degrees. Which is exactly what we know should happen. You're actually seeing it happen now, graphically as well, because of your asymptote. It's approaching 20 degrees. Good. And you can't go below 20 degrees, obviously. Right? Good. That makes sense, doesn't it? Done. That's it. That's really as hard as it gets. And that was part of the extension 1 year 12 course. So they just added an extra variable, but it's not that, I mean, the math doesn't really change. Here it is, 2008 extension 1 HSE. I might just give you guys, I don't know, maybe 5 minutes just to try that on your own, actually. And then we can do it together. So I doesn't change. And then we'll do double I. Really try it out. Okay, a turkey is taken from the refrigerator. Its temperature is 5 degrees when it is placed in an oven preheated to 190 degrees. Its temperature after T hours in the oven satisfies this equation. Show that T satisfies both this equation and the initial condition. Okay, I think you guys get it, but I'll say it one more time here. Look, oven preheated to 190 degrees. You understand that this temperature of 5 degrees is going to get to the constant 190 degrees. And that's why that A is 190 there, right? So that makes sense and that's obvious. But just so you know, it can't get higher than 190 degrees unless you turn up the oven. And that's what that extra A term there is. The initial condition just means when time is 0. When time is 0 now, if I sub it in, you get 190 take away 185, which means the temperature is 5 degrees, which is exactly what we know. So to do that bit first, if you want to get that out of the way, initial condition, time is 0, you always get your temperature. I'm not worried if you didn't get this bit out or didn't write it because you didn't know to write it. 190 take away 185 is just 5 degrees. So the temperature is just 5 degrees, and that's true. But satisfies this equation now, we have to actually differentiate that. Anyone able to get it out? No? Nobody? 185 K E negative KT. Then you can see it needs negative K, but I've only got a K. So I'll factorize a negative out. I'll factorize a negative K out. So I'm left with negative 185 E negative KT. And then I can see negative 105 E negative KT is T take away 190. And then I'm done. Any questions about this line right here, these three? Pretty easy, right? Double I. The turkey is placed into the oven at 9 a.m. At 10 a.m., the turkey reaches a temperature of 29 degrees. The turkey will be cooked when it reaches a temperature of 80 degrees. At what time to the nearest minute will it be cooked? 3 marks. Okay, so the formula you've got is obviously this. I think we get that. What letter do I have to solve for first?
K.
K, that's the logic, always. K first. So the first thing you've got to do is get rid of time and get rid of temperature. Well, you know that at time is 1 hour because it started at 9 a.m. In 1 hour, the temperature was 29. So when T is equal to 1, capital T is equal to 29. Right, 29, yep. Just plug it in and solve. You'll obviously, because you just got rid of capital T and little t, you'll solve for K. Once you find K, then it's pretty easy after that. 190 minus 185 E negative 1K. Okay, then you just do what I just said, right? Subtract 190, divide negative 185, log it, divide by negative 1. Let's see if we can get the K value out again on our calculator. 29 minus 190, divide negative 185, log answer, divide negative 1. I got K being this on my calculator. I'll just wait a little bit for you guys. Confirm 895. Let's do it there. And then shift store A. Locked it in as A. So the difference between, I don't know, the 2-unit questions that you probably just saw before, so the basic exponential growth and decay compared to Newton's laws of cooling. With Newton's, They don't tell you, hey, go find K, now go find A, now go find B, and then go find T. It's just go do it. So it'll become like this. And you've got to know, okay, I've got to find K. If I don't have these two, I've got to go find these two as well. And then slowly get everything out. So just be aware of that. So anyone having problems getting out this K value? No, we're good. All right. So then the last bit says, the turkey will be cooked when it reaches a temperature of 80. What time would that be? And see how it says nearest minute? So we're going to see this one. But anyways, reaches temperature of 80 degrees. So 80 equals 190 minus 185 E. Now I'm going to do it again. I'm going to use this value, and I'm going to use my A value and see if it mattered. So the first one is, we're going to do the proper answer. Divide by negative 185, log it, divide alpha A. Three hours and 44 minutes. The other one, 80 minus 190, divide by negative 185, log it, divide by negative 0.13895. No, didn't matter in this case either. Good. All right, any questions? Did I get full marks?
When you guys say like time,
So what do you mean?
like 10 o'clock or something like that.
Yeah, that's it. That's the right. So the question says, at what time? It started at 9 a.m. and you had to actually say at 12, 10, 11, 12. At 12:44 p.m. it's ready. You've got a perfectly cooked turkey. And by the way, just so you guys know, this is actually true. If we're talking about really high-end restaurants, fine dining, professional chefs, they actually do. If it's not them themselves, there are mathematicians behind the scene that actually calculate for this particular bird or for this particular meat or whatever it is, whatever you're cooking, if it's seafood, whatever it is, to cook it at the perfect temperature, at the perfect weight, at the perfect consistency, so that it's always consistent, it's always the exact same every single time, and it's cooked exactly the same way you want it all the time. And yeah, so to get perfection, that's when calculus comes in, what we've talked about before. But this is actually used. I do know a chef that actually does use this. Famous chef, anyways, Heston Blumenthal. You probably have heard of him, who uses science and math to actually cook everything and make everything perfect. So it is used, and there it is, anyways. And then you can do it again. I don't really want to do another one again like that. Let's see. Sydney grammar. Sydney grammar means a little bit harder, so maybe we'll try that one. And that's it. That's the last one. Let's do that. How are we going for time? I might leave this as a revision question for next week then. What I'll rather do is just get started on what we're going to look into next week. So I'll stop the recording now. Oh.